Hello, everybody, and welcome to the first unit on Introduction to Engineering Design and Manufacturing. This will overlap to include Engineering 3 students, just like the last presentation did. After this week, or this assignment rather, there will be one more that kind of groups everyone together, but then beyond that, and really beyond this week, by that time, it's going to veer down two separate pathways. Alright, so let's go ahead and get started. I'm going to swap this out so you can see. And again, for the Engineering 3 students, this is going to be somewhat of a review, but that's okay because that's part of the intent here. We're just going to nail down some career pathways and define them in a specific way. And I really want you to, especially the Engineering 3 students, you really want to take advantage of this exercise to really try to bore in on what it is that you would like to do. And it's not only going to serve you for sake of this project that we're about to embark on in the way of a presentation, but also for designs very soon in the adventure. So design engineering. Basically, there are two types of roles, that of technicians or detailers, that come out of junior college. They are, in many ways, supporting roles to that of four-year degreed engineers, but they are in every bit as much of a demand as four-year engineers are. All they are is they're working in support roles as opposed to the lead roles. Again, what we're looking to hope we find here is a way in which you can identify yourself in a particular career pathway that goes beyond just design engineering, but to a specific industry. There are several branches that we're going to start off by introducing, but then we want you to really do a little research, especially the Engineering 3 students that I'm going to hold to a higher standard here in identifying more specifically what it is that you're looking to pursue. And again, this is not just for sake of a paper. This is for sake of, eventual projects that we personalized down the line. For example, engineering services. You could be in a service-related engineering type role to include civil, electrical, mechanical, marine, manufacturing, petroleum. Now, when you're in that type of role, you're a support unit for any number of different types of industries. That's going to be up to you to define. Now, those industries can come out of nuclear engineering, automotive engineering, biomedical engineering, the list goes on and on and on. You start out by finding what it is that you like to do, and then we go from there. If you enjoy machining, there's a whole slew of machine tool design, tool and die type roles that are out there, and those two can vary. Maybe not as broad as engineering design services in general, but they can reach far and wide as well. Aerospace service technicians. We're going to have somebody from PIA who you've already met before that can speak to that. But there again, service technicians. What would you need out of that trade school, basically? And then, of course, like any of these roles, you can pursue higher level from there. Master machinist is not all that unlike a CNC machinist. That would come away with, at the outset, skills that would allow them to run that machine in the back of the room. However, a master machinist basically takes that to a journeyman level, to where they're very quick on their feet and they're adaptable to new creative designs instead of working off of an existing design. And then, lastly, manufacturing technicians and engineers. This is by and large what people start off doing here locally with respect to Corning and GE. They learn the trade and they learn the output required of them on the job, and then with that, it can spearhead them towards an education. The branches of engineering that are more, that the prior slide of technicians can speak to, are more required of a four-year or advanced level engineer. And they include aerospace, architectural, civil, electrical, and the like. These are familiar to you only because you can identify with those bullets. You just haven't necessarily delved that deeply into the roles that fall within each. From a mechanical perspective, I can tell you from past experience that typically what that means is designing of machines and devices and also designing fixture and work holding devices. That's the type of work that I've been involved in. And that leads us to the manufacturing engineering. So not only will you be responsible for those aforementioned mechanical engineering type requirements, but you'd also be responsible for initially working with design intent to figure out how something gets made. And that's not only just in the prototype phase and concept, but also with respect to the finished product. So that can make for many, many different iterative runs of product, to include rapid prototyping, which is basically just cutting something quickly out of a less expensive material just to get proof of fit down or concept down. And that's when you come away with the design intent. And again, design intent and the deliverable stage can vary over a product life cycle from anywhere from many months to many years. Projects oftentimes get shelved and revisited later because of the findings that come out over a product life cycle. They are often collaborative with cross-functional teams to include far more than just a manufacturing or a mechanical or a lead design engineer type roles. They would also include marketing, quality, and sometimes even legal. Manufacturing engineering is also responsible for the basis of all new product in the pipeline. So you have to know your manufacturing to the point where you can vet the product for manufacturing at the outset. You got to determine whether or not the design is even fit for manufacturing. So that's why there's a lot of collaboration that goes on in cross-functionality between manufacturing, design, business leads, as well as marketing, quality, and the like. Because you've got to be able to make sure that your costs are properly aligned with the business case, because otherwise you could be making something for a loss. And then you typically are responsible for mapping out the life cycle of that product, all the way from process flow through to verification and validation. Manufacturing engineers also are responsible for 3D laser scanning, and currently there's a lot of reverse engineering going on in the industry. It evolved from a coordinate measuring methodology of machine 3D scan or with a stylus, or either that or a laser reader, where you're actually measuring parts by scanning them and then bringing that information back into a CAD system. Reverse engineering, to be specific, creates a drawing from a completed part, and again, you can take it from measurements or you can use the extensive measuring system that we just talked about. Parametric modeling within the manufacturing scope also requires, and what we've had experience with in Engineering 3, with the Engineering 3 students, is that 3D solid modeling kernel with attributes to include dimensions, material density, and imported data. By that I mean you're able to determine center of gravity, specific density, and weight to an object once it's completely defined in a parametric model like our Autodesk Inventor. You will be able to support assembly design, especially Engineering 3 students that will get into some accelerated and more in-depth complex assembly methods. And you'll also understand how you can make for modifications without starting over. In other words, parametrically assigning sketch variables as opposed to hard values. And its current standard is supported by geometric dimensioning and tolerancing. Manufacturing engineering also includes finite element analysis, material study for mechanical and chemical composition. More often than not, you need to make sure that your materials have passed inspection. And that can be not only the raw material, but also the microstructure or the compacted material once it's gone through a forging operation. That's what's typically used in knee and hip screw press type operations for the orthopedic industry. Exotic material strength testing, often in the raw materials stage, can be accomplished by tensile testing or dynamic testing, where you're actually bringing the material to a point of failure. It also allows for experimental materials where applicable. Thermal studies are typically conducted by, while they can be included in a 3D model like Inventor, they're typically handled at a higher level with third-party software like ANSYS. And again, what you're allowing for here is modifications without having to start over. Finally, we have rapid prototyping and additive machining. Case study of process development once the design is frozen. It begins with a sketch, it continues with the model, and it then leads to machine code to generate cutter path for either 3D printing or machining of materials. And then lastly, ergonomics, the feasibility of the design in the hands of the end user. This is important to understand from our vantage point because, again, we're going to be involved with a lot of 3D machining and 3D printing here. You export it into an STL for sake of a plastic component. 3D plastic printout, while it doesn't have necessarily the correct weight of the end product, it has a desired shape, and you can run them in small batches to get the ergonomic feel and functionality intent. And then next, we would rapid prototype on the machine with a lower cost material than the end material, maybe in aluminum. And finally, with rapid prototyping, you can run verification, validation, leading to a limited market release. And then full launch. I bring all this up because I also wanted to lead to this assignment. And that is where we're going with this. You understand now the engineering services, the types of roles that can be defined, either 2-year, 4-year. You understand a little bit about aerospace, machine tool designers, and machining. What I want you to do is I want you to create a website or PowerPoint to define these engineering design roles and finding examples of each. Then, either in an adjacent connected PowerPoint or a separate PowerPoint altogether, create another one to include not the roles any longer, but the processes, to include those of what we just described within those manufacturing engineering slides. Each section must contain a process or a role definition, the image, and at least 2 parts that are made by that process or job title. And then lastly, be sure to create 1 page at minimum, that basically boils down to a skilled trade or degree position of the above, or something not listed that you would like to expand on. And the reason why you're choosing a role is not just for sake of fulfilling the obligation of this requirement, but also to really identify with what would be the path that you take. And this will help us a great deal to not only come up with a pathway for you to pursue, but it allows us to establish goals so that we can determine what projects would be best suited for you down the road. And that's everything. Thank you for your time.